Yes,
Yes,
ma'am.
ma'am. Oh, okay. So I was saying that today we will be doing questions based on what we were doing last week. Last week we were doing vectors in 2D. So that's exactly what we will be doing. But before we get directly into that, I wanted to remember there was a question that we were doing last week, and I tried explaining cardinal directions, right? And then I couldn't fully tell you why. You'd have to put it in in that specific manner, right? So that's what I wanna firstly talk about. Then we'll move on to the questions, right? The cardinal directions. Okay. Um, right. So if this is your north, this will be your south, this will be your west, right? And this will be your east over here. Okay. If you have an angle and it's over here, right? This is your angle. It's over here. Let's call it theta. When you look at this theta, you are moving from the north, going where? Going to the east. Do you guys understand that? Like you're moving from this north pole, going where? Going to the east, right? So wait, okay, let's say for theta, what's actually happening? You are moving towards the east from the north. So it's going to be what? If you're moving from the east, you're going to the east from the north. We're going to call it east of north. That's the direction in which you're moving at. So theta, it's placed in a position whereby you're moving east from the north. Do you understand that? Like you're moving east from where? From the north. This is me trying to explain how you're moving, right? So if the theta angle, bear in mind, it's not here, it's here. It's over here, right? You're moving east from the north. So how you would write it down, it would be, you'd say it's because you're moving east from north. So instead of this from, you're just going to write it as east of north, which still makes sense because you're moving east from the north, right? Let's make another example. Now, let's say you have theta 1. You're moving that way. Now, what are you actually moving? Where are you moving? You're moving where? You're moving north from what? From east. So you're moving north from east. Where are you currently? You're currently at east, but you're trying to reach the north. So you're moving north from the east. So for theta 1, it would be what? It would be you're moving north from east. So when you write it down, you just say north of east. Do you guys get this?
Yes, ma'am.
Okay. And how you'll just be able to tell it's if whether the angle it's on this side or it's on this side. Because if it's on this side, it's moving towards the north. But if it's on this side, it's moving towards the east. Okay, let's have another example. Let's say you have an angle over here. Okay, let's say you have an angle over here, right? And this is beta. Let's say this is beta, and this is beta 1. Okay, fine. Now I need you to try and explain the movement of this angle over here. So for this angle over here, how are you moving? You're moving west from where? From north. So you're moving west for this one, for beta, right? For beta, it will be you're moving west from the north. Do you understand this? You're moving towards the west, but where are you currently situated? At the north, right? Then for beta 1, which is this one, B1, it will be what? You're moving the north from the west. Okay, wait. Back to beta. See, I just wrote you're moving west from the north, but this is not the actual way to write it. You would then properly write it down as west of north. Now let's look at beta 1, right? Beta 1, you're moving where? You're moving towards the north from the west. So for beta 1, which is this one angle, you're moving towards the north from the west. So you're moving north from the west. So then this would be north. You're moving the north of the west. Do you guys get this? Do you guys get this?
Yes, ma'am.
Okay, great. Now let's do the last two. Um, Okay, now let's look at this one, which is this one. Where is it moving? It's moving south from the west, right? So it's moving south from the west. So how you'd actually write it, you'd say this is what? South of west, right? Now let's look at A1. A1, it's moving towards the west from the south, right? So with A1, how it differs is that it is moving west, sorry, from the south. So how you'd actually write it down, you'd say this is just west of south, right? Now let's do this one over here. Um, yeah, let me just- mm, let's say you have C1 and you have C2. Let's look at what C2 is doing. C2, which is this one, it's moving south from the east point, right? So for C2, you would say it's moving south from the east. And I mean, it's making sense because it's going that way. It's leaving the east, going towards the south, right? So you then say south of east, right? Now let's look at C1, which is this one. It's leaving the south, going towards the east point. So if it's going that way, it's leaving the south. We're going to say it's going where? It's going east from the south. And how you'd properly write it is just east of south. Do you guys get this? Like, because I don't think the last time I properly explained why, but this is the reason, and this I think is the clearest explanation as to why it would now be maybe south of east. Because if you look at this C2, it's leaving The east going to the south. So it's moving south from the east. So you're going to write it as south of east. Is that does that make sense?
Yes, ma'am.
Does everybody understand besides ah,
Yes, ma'am.
okay, great. Okay. So this is our first one, right? So wait, let me do this. Mm,
Uh-huh. Please come open the disc. The disc. Yeah.
um wait, nah. I just need to okay, so next thing we're going to try to find the resultant force using scale drawing, right? Remember last week we spoke on scale drawing where we said that scale drawing is when you would set. Okay, good. We're on the right track. Okay, remember last week we said scale drawing is when maybe you have a force, they're all acting on a particular object at angles, right? And they have maybe for scale purposes, you would then have to specify that 1 centimeter equals to 1 Newton so that you'd be able to draw your your forces, right? Either as a parallelogram or sorry, something, right? So now we have to find the resultant. This is what we're doing. Resultant force using scale. Okay, because remember last week we learned how to find the resultant force mathematically if we have a right angle triangle, and let's say here we have 5, here we have 2. We know that the resultant force is going to be given to us by what? By Pythagoras theorem, right? But over here, we are told that find the resultant force using scale drawing, right? I sent out an announcement on the group because I was like, please, when you join today, make sure you have your protectors ready. This it was for this particular question. Ne? So yeah, let's do it. Okay. Mm, okay. Yeah. But they won't be. Okay. We have 30 over here. And then we have 40 over here, right? This is F1, which is equals to 250 Newton. And we have F2, which is equals to 350 Newton. So we're required to find the resultant. Okay, we have force 1, which is 250. We have force 2, which is 350, right? And we're required to find the, what do you call it? We're required to find the resultant force using scale drawing. Okay, fine. Now, this is where your protector is going to come in because at first you have what? You have angles. Make note of that. You have angles, so you'd need your protector to be able to measure out where a particular angle is, right? So we're going to make a dot over here. First thing first, you make a dot over here and just place a protector over here. Now, on your protect, the protector, protector. Oh my goodness. On your instrument, right? You have to, because look at this. They said that for force one, it's elevated 30 degrees upward, right? Oh, wait. Sorry. First things first, before anything else, you have to create a scale. So, because see, we have like multiples of 50s, we could say 1 centimeter equals to 50 Newton, right? So this is going to be our scale. So that we know when we're plotting, this is what we're referencing, right? So okay, cool. We have our dot over here. We're going to go to our protector because it's elevated 30 degrees upward. We're going to look for 30 where towards our right here, not this side. Towards our right, we're going to look for a 30. The 30 it's supposed to be somewhere over here. I hope you guys are following, ne? Okay, so if a 30 is somewhere over here, remember F1, it's what? It's 250 Newton. We said 1 centimeter equals to 50 Newton. So let's find out what 250 Newton would be in what? In centimeters, right? So it's going to be an X over here, right? Then we cross multiply. So it's going to be X. Let me just continue writing here because what if our drawing goes that way? So it's going to be X50 equals to 250 divided by 50 on both sides. Do you guys understand why I'm doing what I'm doing currently? I'm just trying to find what 250 would be in terms of centimeters, because remember we set the scale for 1 centimeter to be equals to 50 Newton, right? This is 50, don't be. So if we divide 250 by 50, we have 5, right? Yeah, because it's going to be 5, 10, 15, 20, 25. Yes, we're going to have x equals to 5 centimeters. So 250 Newton, it's the same thing as 5 centimeter, according to our scale, right? So when we plot, remember that, okay, this is our centimeter section. Okay, fine. Remember we said that this is where, because this is sort of like like the straight line, the imaginary straight line that we have, right? This is where our 30 degrees would be. But from this dot all the way to where it's going to end, it has to pass over this dot, and it's supposed to be where? At 5 centimeters. Because remember, we said 250 Newton is equals to 5 centimeters, right? So it would be over here. So this is our 5 centimeters. I'm not lying. Yes, this is F1, which is equals to 5 cm. Now let's go to F2, right? Now, because F2, it's in the, like, because if you were to look at this is the upper section, this is the lower section, right? Because our F2, it's in the lower section, you have to tilt your protector. So because it's 40 degrees, right? It's placed at 40, we have to look for 40 to the right. So this is where 40 would be over here. Now, before we even connect the dots, we just have to figure out what 350 would be in terms of centimeters. Remember, we said 1 cm equals to 50 Newton. Then you don't know what the centimeter would be in terms of the 350. So you're going to put an X over here equals to 350 Newton. Then you cross multiply, right? So you're going to have X 50N equals to 350. So you're going to divide both sides by 50. You're going to divide both sides by 50. So our X will be equals to, what is 350 divided by 50? 5, 10, 15, 20, 25, 30, 35. It will just be 7 centimeters. So which means our F2 will be equals to 7 centimeters. Do you guys get this?
Yes, ma'am.
Okay, great. So now when you connect, you're going to go back to your dots, right? It has to go all the way to what? To 7 centimeters. Here's your 7 centimeters, right? It's going to go out. What? Now, remember, remember over here, we have what? Because at we had a 40 over here plus a 30. So which means this angle is going to be what? The 40 plus the 30, which is going to give us 70 degrees, right? So remember a parallelogram. What do we know about a parallelogram? Because this has to be a closed up parallelogram, but we have to figure out what this angle should be in order to be able to close it, right? So we know that with regards to a parallelogram, opposite angles they add up to what? To 180, right? So if this angle over here it's 100, it's sorry, if this angle over here it's 70, it means that the angle over here where you're going to place your next line, it has to be 110, because these two angles they add up to 180, and we already have 70 being here. Do you guys get that?
No.
Okay, remember we have two um two forces, right? One is acting that way. This is your F1, this is your F2, equals to, what do you call it? This is 7 centimeters. Because we're trying, they said the initial question was saying find the resultant force. We know that if we have it like this and we're trying to find the resultant force, what do we just do? We have to complete a parallelogram, right? In order to find the resultant force. Because this is the tail to tail method. And the only way to find a resultant force using the tail to tail method is by doing what? Is by completing the parallelogram, right? That part you understand.
Yes, ma'am.
Okay, fine. Now I'm saying in a parallelogram, because this is a scale drawing, this is done accurately. Remember in the past examples, we would just assume that, okay, fine, if my F1 is going that way and my F2 it's going that way, in order to draw a parallelogram, we would just draw lines, dotted lines like this, like this, like this, and assume that FR would be going that way. But because the same method applies over here, the only thing that's going to differ now is that this is a scale drawing. It's drawn like accurately. So what we know about the parallelogram is that these two sides, because a parallelogram, it's your shapes like rectangles, squares, and everything like that. If you take two opposite, directly opposite, né, right? They will add up to what? To 180. That's what we know about a parallelogram. That these two angles, they have to add up to 180. And already we've concluded that we have 70 here. Where do we get the 70 from? We get the 70 from 40 plus 30 over here. Do you understand why then now if this is 70 on the opposite side, we'd have to have on the opposite side we'd have to have, sorry, what do you call it? We would have to have 110.
Yes, ma'am.
Okay. Then again, you go, because we want this angle to now be 110, right? You go, you take your protector. Okay. Wait, this is 70. Yeah. Sorry, no. Okay, fine. You have your thing over here. Okay, let's look at where our. Did I draw this accurately? Let me just see. Wait, no, let me just check. One, two, three. Yes, it is drawn accurately. Wait, wait, now I'm trying to find out how the resultant would then look. No, not the resultant, the closing thing. Oh, yeah. Sorry. Fine. Now you have your F1. At the end of F1, you place what? Your protector, like this, not like this. This way, because you're trying to measure out 110, right? So when it's this way around, you go to where your 110 is. It's over here. Can you guys see it? Where your 110 is? Well, on your protector, because now I don't think it's that clear. But let me just take it down and bring this over here. Okay, but when it's like this, you can see that here's your 110, right? Over here, here's my dot. You see it? So, because now this angle, if you were to connect it like this, and then you met, okay, wait, let me just draw it out. So it would be a dotted line. It wouldn't be a straight solid line because you're just trying to complete the parallelogram. So this is what it would look like. A dotted line going that way. It has to pass over your dot. I think mine went below the dot, but yeah. And then from here as well, from here as well, you'd have to measure your 110 because this angle also has to be 110, right? Two opposite angles, they have to be equals to what? They have to be equal to 180. So this over here, you place your protector at the end of it. So your 110, when you look at this, your 110 would be somewhere over here. Wait, somewhere over here, right? So then you'd have to connect the end of this F2 with this dotted line. So it would go that way. Can I add somebody now? Oh, so no way. Okay, so you'd connect these like this. Okay, fine. So if you were to take your not calculator, protector, and measure this, it's going to give you 110. This would also give you 110. This would give you 70. Right? Fine. Okay, cool. Now that you have your F1 going in that direction, your F2 going in that direction. Remember, for the resultant force, you have to draw from the tails of the two forces to the intersection of the end of the parallelogram, right? So your resultant force is going to look like this. Your resultant force is going to look like this. So because now they said find the resultant, because they had stated that find the resultant force using scale drawing, this resultant force over here, in order to find its magnitude, this is what you're going to do. You're going to use your ruler, measure it up, see what it is on your ruler, right? Because when you look at it on your ruler, it's giving me 9.56. Let's say 9.6. So our resultant FR equals to 9.6 centimeters, right? But remember, in the scale we had said what we said, 1 centimeter equals to 50 Newton, right? So if we have 9.6, we have to find its magnitude in force terms, right? So we'd have to cross multiply. So it's going to be 50 times 9.6 equals to x. Can somebody say 50 times 9.6 for me on their calculator?
480.
480 Newton. So our FR would be 480 in newtons. Do you guys understand this and how I came about to draw this? Like if I were to ask you, please draw this, would you be able to draw it?
Ma'am, I want to ask the values used in the protractor, like which one do you know how to use? Like there's those inside numbers and then the outside ones.
Um, where? Here. Here.
Like on the on the instrument, I mean.
Or on the instrument.
Yeah, I wanted to ask which numbers do you know when to use, like the inside
Okay.
numbers or the outside?
Okay. Thing is, this is the chat with the protector, ne? Um, let me take this paper over here. So what you're asking me is if they said look for 40, because okay, fine, let's assume this is your dot, right? This is the point of reference that you're drawing from, this dot over here. And you're saying if they gave you this angle right here, right, this 30, because this is your x-axis, see this 30, how would you know if you're supposed to choose the 30 from this point or this point over here? That's what you're asking me, right?
Yes, ma'am.
Okay, I need you to understand that to your right, it's for acute angles. Acute angles are basically angles that are less than, that are not, okay, acute angles, angles that are less than 90, they would move towards your right. Because if you draw from this 30 over here, you put it here, right? And then you do this is giving you a 30, which is what's directed over here. But if you take it from here and you draw this 30, it would be towards the negatives. And not just that, if you're measuring with relative to your y-axis, it's going to give you, wait a minute, it's going to give you this angle over here, right? Wait, let me look for another explanation as to why we take the ones from the 30, not the ones from the right angle, for the ones from the right side, not the left hand side. Let me open my computer. Let me just try and find a proper reason, so that I don't make you get lost in the midst of it. baseline. So they're saying the baseline is drawn horizontally to the right. So the 0% mark on the right is correct from the starting point. That is why it seems like angles. If you read from the wrong scale, um, okay. So they're saying we measure from we measure from the right. Reason being, we base it off of the horizontal x-axis. So if you were to measure from the left, you would get the supplementary. I mean, which makes sense because if you look at your 20 on the right hand side, you plot down on the 20, it's going to give you 20 degrees from the right hand side. But if you go to the other side and you try and plot at 20, it's going to give you 160. And if we have 160 plus 20, this is 180. So the left hand side, if you were to draw from the left hand side, it's not going to give you 20, but it's going to give you 160. Reason being, you are referencing from this horizontal x-axis. Do you get it? So if you, from the horizontal x-axis, if you want 20, you're going to get this. This will be 20. But if you place this over here, on this 20 on this side, and our reference point, it's this horizontal x-axis, it will no longer be just a 20, but it will be a 160-degree angle. Reason why it's a 160-degree angle is because they are counting from the horizontal x-axis, right? That's the reason
Yes,
as
ma'am.
to why we are choosing from the right instead. I think that makes sense. But if it doesn't, I'll just check further and further as to why we look from this side and not this side. But what they're saying is that if you measure from this, because our universal reference point would be the horizontal axis. But I'll check if we have questions whereby they would require for us to now measure from the other side. I think that would be interesting to look at as to see how different it is from this one. Né? But so far, do you understand this one?
Yes, ma'am.
Okay, great. I'll look it up, ne? I'll definitely look that one up and I'll send the reason maybe like tonight or something on the group. Um okay, so this was the tail to tail method, right? So we're going to try and determine the resultant force using the head to tail method now. So okay, fine. Um head to tail. Using the head to tail method. Right. So let's say we have these forces, right? Acting along its axis. You guys can still see my screen, right?
Yes, ma'am.
One is going that way, the other one is going that way, and one would be going that way. And how this differs is that the previous one it was a, what do you call it again? It was tail to tail. This is a head to tail, right? So Okay, so wait, we have 20 degrees for a 7 Newton force. We have 30 degrees for a 10 Newton force. And we have 6 Newton for a 40 degrees. Right? And they're telling us to use what? To use the head to tail method. Right? So now let's look at all these forces and the direction in which they're acting in. This one, let's say if this was a Cartesian plane, this one would just be moving that way, and this one would just be moving that way, and this one would just be moving that way. So our responsibility in this question is that we have to put them in a head to tail type of setup. And what I mean by the head to tail, sorry, what I mean by the head to tail is that the head of one should be at the tail of one, because this is the tail to tail. No, this is the head to tail. This is the head. This is the tail. This is a head. This is a tail. So we're required to do this, right? Now, this is how you're going to do it, because you have to use scales, scale drawing. Sorry. So let's choose our what our measurements are going to be. 1 cm will be equals to um because we just have 10, 7, and 6. I think 1 centimeter should just be 1 Newton, right? So now let's check how we can plot this. Wait a minute. Okay. Uh-uh. Wait, let me. Give me a minute. Protect it. William. I think. Oh. Okay, now look at that 7 Newton force, right? The 7 Newton, it's moving like upward, kinda, at an angle of what? At an angle of 20. So, first things first, we have to have our starting dot. Like, let's just put it over here. Now, look at that 7 Newton. It is placed at what? At a 20-degree angle. So, even when we're drawing over here, we have to place our protector here. And let me just do this. When we place our protector here, we have to check where is our 20, right? Because they said it's 20 Newton, the 7 Newton one. Here is our 20. So you draw another dot over here. Fine. So you have to connect these two dots, but remember we said 1 centimeter equals to 1 Newton. And we currently have what? 7 Newton for our F1. So which means 7 Newton will just be what? 7 centimeters. Right? So you go to your ruler, put it here, join the two dots until it's 7 centimeters. So this will be your 7 centimeters over. Wait, I was just trying to show the arrow, right? So this is our F1, which is equals to 7 centimeters. Okay, cool. Now let's look at the second one, right? The second one, which is what? The 10 Newton one. How is the 10 Newton one acting? The 10 Newton one, it's acting. Sorry. Here's your 10 Newton one. The 10 Newton one, it's acting. Well, which one should we start with? Let's start with the 6 degree one, right? The six, sorry. the 6 Newton one. Yes. You're going to take a protector, right? Place it like this again. No, like this. Because it's in the downward force. Um, check where your 40 is because it's at an angle of what? It's at an angle of 40 degrees. So at the end, at the head of the first force, you'd place your protector like this, and then check where your 40 is in order to be able to draw this 6 Newton force, right? So here is your 40 over here. So all that you have to do now is what? Connect these dots, right? So when you connect the dots, they said it's 6 Newton, and remember we said 1 centimeter is equals to 1 Newton, right? So it would just be like this. You have to connect it until uh you'd have to do this. Sorry. Then this would be your 6 Newton. Do you guys which is equals to 6 centimeters? Do you guys understand how we got F1 and we were able to draw this F2 over there?
Ma'am, the 6 Newton one, does it matter where you place it?
Does it matter where you place the
Yes.
yes, it does matter.
Oh, okay. Oh.
You, yeah, but wait, besides where it matters, do you guys understand why it's like that?
Yes, ma'am.
Does everybody agree with me? Does anybody have a question or something? No. Okay, so you understand these two, right? Good. So now let's go to this one. The what is this? The 10 Newton one. Because it's head to tail, we can from the end of this one, because remember, from the end of we from the head of the first one, we drew the tail of the second one. So from the what do you call it? From the end of the second force, from the head of the second force, we'd be able to draw force number 3 because it's head to tail. So still here, we'd have to have um, tail of the next, what do you call it? Tail of the next, tail of the next force. Either you could put it here, start the tail here, and have the head somewhere over here, or you could put it here, have the head of the 10 Newton, sorry, have the head of the 10 Newton here, the tail somewhere over here, right? So let's do that quickly. You're going to take your protector, place it like this, and then you'd have to make your mark of where 30 degrees is. Because remember, they said it's 30 degrees this side, right? You guys see that? Remember that this is your base dot. This is the dot that you were working with initially. So you just place your protector like this and then try to check where exactly your 30 is. Because this is an angle of 30 elevation, elevated to 30 degrees, right? So you take your protector here, put your dot, and then try connecting this with this, but it has to be what? It has to be 10 centimeters because we said 1 centimeter equals to 1 Newton. And this force, it's 10 Newtons. So which means it's going to be, if it's, sorry, no, I was picking up this ruler. If it's 10 Newtons, it means it's just going to be 10 centimeters. So we have to connect these two until we get to what? To 10 centimeter, right? Let me just do this. 10 centimeter. It would be over here. Remember, this is the head. Okay, fine. So we have F1, we have our F2, we have our F3, right? These are all drawn according to scale because in between it's their respective angles, right? So now, in order to find, sorry. So now, in order to find the resultant vector, all you would have to do now is connect this end to this part over here. What is the reason for that? The reason would be you're trying to find how long this part is. And then after finding out how long this part is, it would be your resultant force. You get it? So you'd have to connect this with this part over here. And it'll just look like this. So this will be your FR. What did we say? In order to find the magnitude of the FR, you just simply have to use your ruler. This FR, when you measure it, it's like four. It's giving me 4, uh, 4,4. So FR would be 4,4 in what? In centimeters. Therefore, FR in its magnitude form, it will be, because we said 1 centimeter. Remember, we said 1 centimeter equals to 1 Newton. So which means in Newton form, this resultant force, it will just be 4,4 Newton. Do you guys understand this?
Yes, ma'am.
Okay. So this was finding the resultant vector. We did the resultant vector using the tail to tail. We did the resultant vector using the head to tail method. Now we're going to remember last week I spoke of something called breaking down um a force into its components, right? So that's what we're going to try and do here. We're going to find the resultant, find the resultant vector. Oh, sorry. Find the result. Wait. Find the result. If you can't see, just tell me. Find the resultant force using component method. Using component method. Remember what we said. Method. What we said about component method is that if you have a force and it's acting in that direction, right? Beta. Okay, this is the north, south, or west. And is this the compass? Yes. Okay, fine. If you have a force of 5 Newton, you can break it down because if you draw this and you complete it and you draw it in a form of a 90-degree angle, this is what it would look like, right? This would be your 5 Newton. And over here, you'd have your Fx, you'd have your Fy. So if you try and break down this 5 Newton into its Fx and its Fy, we said the cos gives us the what? The x. The sine gives us the what? It gives us the y. So this is how it would now look. In order to get your x component, you'd say Fx, this just means the force in the x direction, would be F applied multiplied by the cos of theta. In order to find your y component, it would just be F applied multiplied by the sine of theta, right? So now we're given a diagram that looks like this. We have to break it down into its components, then try to find um yeah. So we have 10 Newton this way, this way, and then this way. This is just a 40. This is a 20. This is a 30. Then this is a 7. And this is a 6 Newton, right? Okay, so this is 7 Newton, 10 Newton, 6 Newton, right? So if we want to break this down into different components, um, if we want to break it down into different, let's just say different components. Okay, let me just use this red color, right? You have to choose directions, right? Either you take up as positive or down as positive, right? You choose up or down as positive, and you also have to choose right or left as positive. In this case, I'm going to choose our up as positive and our right as positive as well, right? So now we have three forces. Let's break down these three forces into its own individual components, right? Now let's look at number one. We're going to deal with the 7 Newton one. So when you break down the 7 Newton force into its components, you're going to have a y that's going that way, and you're also going to have an x that's going that way, right? So for your fx, you'll just have, remember we said fx is what? It's fa, the force applied, multiplied by cos of theta. So for fx, you'll just have 7 multiplied by cos of 20. Can somebody punch this into the calculator for me? Hi.
6,58.
6,58 Newton, right? So this would be your fx for 7 Newton. So because look at it, it's going up. You're going to just say up, right? Indicate up. You'll see why it's going to be beneficial once we come back. So for Fy, it's going to be, may you please also punch this into the calculator. For me, it's going to be 7 multiplied by sine of 20, which is just derived from this force applied multiplied by sine theta. What is this? A 7 multiplied by sine 20.
2,39. 39.
2,39 Newton, right? So it's going to be going to the right. Okay, fine. Now we're done with the 7 Newton one, right? Let's look at this 10 Newton one, right? This is number 2, the 10 Newton one, right? When you break it down into its component, the Fy, it is still going up, but let's look at what's happening to its Fx. The Fx, it's going to the left, right? So for fx, we're going to have, what is the force applied? It's 10 Newton multiplied by cos of 30. Can you please put this in the calculator for me? 10 cos 30.
8,66.
8,66 Newton. But it's what? Wait, fx, it's to the left. Remember that. Because it's moving that way. Unlike the 7 Newton one. All right. So you're going to say left. Now let's look at our Fy. You're going to have Fy equals to 10. Can you say 10 multiplied by sine 30, please?
5.
5 Newton, right? Up. Now let's look at the third force. Let me try and put it here. The third force, we have the 6 Newton force, the 6 Newton one. So for Fx, we're going to have 6 cos 40. Please put this into the calculator for me. This one, its x's, it's going to go to the right. But if you look at the y, it's going to go where? Down, right? Because you're just breaking it down into its components. You guys understand how to break it down into its components, right?
Yes, ma'am.
Okay. So what is 6 multiplied by cos of 40?
4,60.
60. Can you say
Wait, ma'am,
6? Yes?
are we allowed to like round off?
Yeah, you're allowed to round off.
Okay.
So it's 4,60 Newton. Let's look at this fx. It's going to the right. So you'd say right. Right? Now, can you do the fy? Just say 6 multiplied by sine of 40. What is it going to be?
3,86.
3,86 Newton downwards. Because look at how your fy is for the 6 Newton one. It's going down, right? Now,
Yes, ma'am.
okay, wait, I need to find paper. Okay, so we know what FR is, right? We know that the resultant force, it's the sum of, where's that pen? The resultant force is the sum in component. Once you've broken it down into components, FR will just be the fxt plus fyt, right? So we have to find the sum of the fx and then find the sum of the yt so that we can be able to find the fr. Bear with me, ne? So because we have three, so let's say fx total. This is just the component forces in the x axis total, like adding all of them up, right? For the 7 Newton one, remember which one is the 7 Newton one? This one, we said we have 6,58. It's going up, so it's positive, right? So it's going to be 6,58 plus, let's look at the 10 Newton one. The 10 Newton one, Eban, wait, sorry, I made a mistake. It's it's an fx. It can't go up. It's going to the right. So fx, this 6,8, it's going to the right. So it's positive because it's going to the
And
right. Remember? Hello?
for the FX at 10 newtons, it's 9,40.
So it's not 8,66.
No,
It's going to be what? 9,40.
40. Yes.
40. But for the 10 one, we said on the x-axis, it will move to the left, right? So it will be left. Okay, fine. So this one is correct, must the 6,581.
Yes.
Okay, so now let's look at we're trying to find the total forces along the x-axis. Basically, add all the f-x's of all different components so that we can have fx total, right? So we're going to, remember we chose right as our positive. This 6,8 for the 7 Newton force, it's going to the right, so it's going to be a positive. Now let's look at the 10 Newton one, right? The 10 Newton, where's the 10 Newton? Here it is. It's moving, its x-axis, it's moving to the left. So it's going to be a minus. So when we substitute it in here, we're going to say minus 9,40, right? Do you guys understand why it's a minus 9,40? Because it's moving to the right, to the left, sorry. And we chose our right as positive, right? Then we have plus. Now let's look at the x-axis of the 6 Newton one. The x-axis of the 6 Newton one, it's going that way. It's going to the right. So it's positive. So it's going to be plus 4,60. Can somebody put this into the calculator for me?
1,78.
So we're going to have fxt as 1,78 Newton, right? Now we have to, this is our fxt, the total um components of the x-axis, right, for the three different forces. Now we have to do fyt. We chose our up as positive, remember that, right? So for this for the 7 Newton, our y is indeed going up, so it's going to be positive. So we're going to have 2,39 plus, now let's go to the 10 Newton one. The 10 Newton one, it's 5 Newton, and it's going up, as we can see over here. So it is going to be a positive because we chose our up as positive. So it's going to be plus 5. Now let's look at the last force. When we go to the 6 Newton, we can tell that the y component is going downward. So because we chose our up as positive, it's going to be minus 3,86, right? Can somebody punch this into the calculator and tell me what our FYT will be?
3,53.
3,53 Newton. So fine. Now we have our X component and we also have our Y component. We can just um, draw our triangle in order to be able to find what FR. Because this, as much as we have X, FXT, and FYT, these are not our FR magnitudes. It's just the X component and the Y component of the FR, right? So we'd have a 90-degree triangle like this. Our FXT, we said it's 1,78 Newton. Our FYT, we said it's 3,5 Newton, right? Now we're looking for FR. This is the FR. This was just the X and the Y component of the FR. So in order to find the FR, we're going to use what? Pythagoras theorem, right? Because we're going to use the X squared equals to, no, this is R squared. R squared equals to X squared plus Y squared. In this case, what is our FR squared? Is going to be equals to X squared plus Y squared. So still FR squared is going to be equals to, what is our X? It's 1,78 squared plus 3,53. This is a 5, sorry. And this is a 3 squared, which will be what? May you please add these together for me? Say 1,78 squared plus 3,53 squared and give me the answer.
15,629.
15,629. Okay, but because this is FR squared and we're just trying to find FR, we can introduce what? The square root. This 2 will cancel. FR, if you put this 15,6293 under a square root, what are you going to find?
3,95.
Sorry, it's what?
3,95.
3,95 Newton. So you have the magnitude of the FR, it's 3,95 Newton. But they also going to want the direction. The direction you can just find it by what? By using theta. Because remember you have an angle over here. If you're trying to find what this angle is, you have the opposite, you have the adjacent. Which one are you going to use? Remember our SOHCAHTOA, right? So if you have the opposite, which is this, and you also have the adjacent, and you're looking for this, you can just use tan, right? So you're going to say tan theta equals to, let me just say the opposite over the adjacent. So tan of theta will be, what is the opposite? 3,53 divided by 1,7, because this is the direction. Bear in mind, they're also going to want the direction. If they wanted the magnitude of the resultant force, they're also going to want the direction that it will take, right? So it'll be theta equals to 10 inverse 3,53 divided by 1,78. Can somebody put this in their calculator and tell me what theta is going to be?
-63.24.
63,24 degrees. So this will be the magnitude of the FR. This will be the magnitude of the FR. This will be the direction of the FR. Do we all understand this? Do we like all get this?
Yes, ma'am.
Other people, do you guys also get what's happening here?
Yes, ma'am.
Okay, great, beautiful. Now we're going to do one whereby, well, wait. Okay, so now we're going to do one whereby we're just let me see. Okay. We have, this is what it looks like. Okay, now let's look at this one and see how it differs from the ones that we've been doing, right? The ones that we've been doing, we've been given the forces. We knew what the forces were. All that we had to do was what? We had to either use the head to tail or tail to tail to try and find the resultant force, right? But this one there is telling us to DTM. This is just determine, right? Determine F1 and F2 using what? Using trigonometry. Okay, fine. Remember the other day when we were working together? I'm going to try and put it somewhere. Okay, remember the other day when we were working together? I said, provided that you have a triangle and that triangle does not yield a 90-degree angle. Like basically, these are just angles, random angles. And you're trying to find this F1 and this is F2 maybe, but you know this as uh uh let's say this is just alpha, this is beta, and this is just C, right? And let's say this is F1, F2, this is F3. You can use the sine rule. And the sine rule would be what? It would be side divided by sine of the opposite angle. So in this case over here, it would be F1 divided by sine beta would be equals to F2 divided by sine C, which will be equals to F3. Hey, man, divided F3 divided by sine of alpha. This is what the sine rule. This is when we're trying to find out what these sides are. So now, if we look at this, right? If we look at this over here, we're given the downward force. We have F1, which they said F1 was, sorry, they said F1 was, what do you say? What do you call F1? They said F1 was 40. Then they said, no, sorry, this is 45, not 14, guys. It's 45, right? So we'd have to make a triangle using these forces, right? So let's try doing that. So we already know that we have a downward acting force, which is the 400 Newton one, right? So we could start there. Place your dot here. Um, let's use scales. If we have 400 Newton, let's say 1 cm equals to 50 Newton, right? So if we have 400 Newton, we're trying to find what 400 Newton would be in terms of centimeters. So you're going to have an x equals to 400, cross multiply, it's going to be 50, x equals to 400, then divide both sides by 50, right? Divide the side by 50. Our x will be 5, 10, 15, 20, 25, 30, 35, 40. It will be 8 centimeters. Right, guys? Do you guys agree with this?
Yes, ma'am.
Okay, great. So which means if it's 8 centimeters, you're going to look for 8 centimeters on the ruler. So you're going to go 8 centimeters down. All right, so this would be our 400 Newton force. Right now, let's look at that F2. They said F2 is what? Let me just do this. Let me use a different thing. F2, it's at a 90, it's sorry, 90. No. F2, it's at a 20-degree angle with respect to what? Your x-axis, right? So when you get to the bottom of this, you can just draw a straight line like this. Okay, fine. Then take your where's the protector? Oh my goodness. Okay, here it is. In order to be able to draw what? Your F2. Take your protector, right? Place it at the end of this angle over here. Here's your 20. So this is where you'd be making your mark over here. Hey, is this? Yeah, that's the point over there. So you're going to draw, this will just be this point and this point are just going to connect your F1. But remember, you don't know what exactly your F1 is. So you could just draw it haphazardly like this, right? And it will, because you're trying to determine what this angle is. Remember, from here, you know that this is 20 degrees. So this will part over here, it will be 20, right? Fine. Hold on to that thought, right? Yes. Which color am I using? Okay. Then we come here to the end of this one. They said that this one was what? It was 45 degrees, right? So we're going to draw again our lines. Reason why you're just doing lines is because you want to be as accurate as you can when you place your protector. Again, they said this is 45 degrees, right? So you'd have to put this here. Um, try and make it as accurate as you can to a 45 degrees. So if it's here, this part over here would be 45 degrees relative to the x-axis, right? So then you connect these two parts. So now, how am I gonna? Oh my goodness. Okay, okay, this is where my 45 degrees is, ne? Oh my goodness. This is where my 45 degrees is. So if I connect using that, uh, okay, can I just extend this 400 Newton? Reason why I'm extending this 400 Newton, ne, is because remember, as much as we know the 400 Newton angle, we don't know what the other angles are. So it's very much a struggle to try and connect them without the other one overlapping because we don't know really what this is. We don't know really what this is. But we know for a fact that this is 20 Newton. Reason why we know that this is 20 Newton over here is because we drew an x-axis at the end of the 400 Newton and we knew correct. You have to place the protector at 20, measure it to be 20. That's where your F2 would lie, right? And then when you come here, in order to be able to get your F1, this is F2, remember? This is your F1. When you put it over here, you're going to plot at where, at where 45 degrees is. Do you guys understand this? So far, this would be 45, because this is 45. This would be 20, right? So, wait a minute. We know that this is 20, right? But as much as this is 20, I want you to know that it's an outside angle, which means this angle inside would be what? It would be 70, right? Because 70 plus 20 is going to be 80. And remember, angles on a triangle, they add up to what? They like a single angle on a triangle, it adds up to 90 degrees, right? This whole angle, it has to give you 90 degrees. But because outside we have 20, it means inside we have what? We have 70. Does that make sense, guys?
Yes, ma'am.
Okay, so if this is 70 over here, okay, this angle we said it's 45. Remember that, right? So if this is 45, I am going to say that this is 20 because when you add these two together, they give you 90. This angle, it will also be what? 20. Reason being alternating angles, because as you can see, we have the Z for alternating angles over here. This angle and this angle, they will be equal. So if we have a 45 plus a 20, we have 45 plus 20. What is it going to give you? It's going to give you 65, right? Yeah, it's going to give you 65. So this will be a equals to 65. Do you guys understand where this 20 comes from? It comes from it being alternating angles, right?
Yes, ma'am.
Okay. So alternating angles. So this whole angle, it will be equals to 65 degrees. Now, in order to find this angle over here, we're going to say 180 because sum of the total angles of a triangle is equals to 180. So it's going to be 180 minus this 70 over here minus 65. Can somebody put this into the calculator for me?
45.
45. 45. So which means this angle will be what? 45. Now, let's look at this. We know this angle, we know this angle, we know this angle, we know this side over here. Remember what the sine rule was saying? It was saying it's side divided by sine of the opposite angle equals to the side divided by sine of the opposite angles. So now let's say for number one, we're calculating for F1. So for F1, we would have F1 divided by sine, what's the opposite angle? 70 divided by sine of 70 equals to, we know this side over here, it's 400 Newton. So it'd be equals to 400 divided by, what is the opposite angle of this 400 Newton? It's sine 65. Sine 65. So now, in order to find the F1, we're going to what? We're going to cross multiply. So we're going to have F1 multiplied by sine of 65 equals to 400 multiplied by sine 70. Sine 70, right? So we're going to have F1 being equals to, we can divide both sides by sine 65 degrees, right? Divide this also by sine 65. So we'll have F1, this and this will cancel. So you're going to have 400. So we're going to have 400 multiplied by sine 70 divided by sine 65. Can you please put this into the calculator for me and tell me what it's going to give? Can somebody do that quickly for me?
414,73.
Sorry, you were saying the answer is going to be what?
414,73.
So that means F1 is going to be 41,73 Newton. Now I'm going to need us to calculate. So we found F1 to be 41. You said 414, right? 414,73
Yes, ma'am.
Newton. Now let's find F2, right? So F2. So let's look at F2. F2, we're going to have side divided by sine of the opposite angle. So we're going to have F2 divided by, what is the opposite angle? Sine 45 divided by sine 45 equals to what we have. We know this side, we also know this side. So you could either go equals to 414 divided by sine 70. Let's just do that, right? Equals to 414,73 divided by sine of 70, right? So for F2, you're going to have to cross multiply. So you're going to have F2 multiplied by sine of 70 equals to sine 45 multiplied by, sorry, 414,73. May you please put this into the calculator for me? Divided by sine 90 divided by sine. Let me just find a clean place to write that. So we're going to have F2 looking like this. It's going to be sine of 45 multiplied by 414,73 all divided by sine 90. Can you put this into the calculator for me so we can find our F2?
293,29.
293,29. So this would be your F2, which is you're saying 293,29 Newton, right? So we found our F1, we found our F2, we answered our question. Does everybody understand this? Like, does this make sense?
Yes, ma'am.
Are you guys certain? Okay, well, yeah, this is this. We will be doing more questions based on this, but not now. Now I'm
Ma'am,
going to, yes.
what's like more confusing is gonna entire sign A cos and 10 in that formula that you showed on that other page.
Wait. The sign rule.
Yes, yes.
Okay. So the sign rule, let me just make a big triangle over here. The sign rule, ne, we mainly use it if we have a triangle that has that's not a 90-degree angle triangle. And so you can't use the Pythagoras theorem to find the other sides, right? So it's actually quite easy. Let me try and explain it. So you have okay, you have, remember we said these angles, they're not what? They're not equals to 90 degrees. So let's say this is alpha, this is beta, right? And let's say this is just theta, right? And we have side, let me call this side A, side B, side C, right? So what the sine rule tells us, this is the sine rule. What the sine rule tells us is that side A, side A divided by sine of the opposite angle. So it would be, this is side A, right? Divided by sine of the opposite angle. This is the opposite angle of A. Do we all agree to that? Like this theta, it's opposite to the side A, right? Like they're opposite, right, guys?
Yes, ma'am.
Okay, so it would be, in order to find side A, you're going to say side A divided by the sine of the opposite angle. In this case, what is opposite to side A? It's theta, right? So you're going to say side A divided by sine of theta equals to, all these, they're like ratios, right? So you're going to say side A divided by the opposite of sine of the opposite angle, which is sine theta, equals to side B. What is the opposite angle of side B? It's alpha. So you're going to say equals to side B divided by sine of the opposite angle of B. What is it? It's alpha. Reason why it's called the sine rule is because you keep on dividing by the sine of the opposite angle, which is all equals to what? Side C divided by, what is the opposite angle of side C? It's just sine beta. So you're going to say sine of beta over here. Now, let's say you're trying to look for this angle over here, and then you have side B. If you know the magnitude of side B, let's say this is 5 Newton, right? And you know this is just F1. In order to find this F1, you're going to say the unknown, which is F1, divided by sine theta. It's going to be equals to, you have to choose a side that is known. You can't have F1 sine theta equals to F2 and they're both unknowns. No, because you at the end of the day, you have to cross multiply. And when you cross multiply, this F1, which is this side that you're looking for, should be the only unknown, right? So that you can be able to find it. So you're going to have F1 divided by sine theta equals to what? It's equals to this, which is a known side. You're going to say it's equals to 5 divided by sine of alpha. Then you'd be able to cross multiply and then find what your F1 is. Is it like a little clear now? Like how this happens, like how this came about?
Yes, ma'am.
Okay, great. Remember during the week, I don't know, when was it? I sent on the group because we were left with like a few minutes. On the group, I sent how we would draw free body diagrams, right? Can we all go to that document? And for the girl that just joined, I'll just resend it to you now. Free body diagram. So a free body diagram, it's just a representation of all the forces acting on an object, right? And the free body diagram, unlike the force diagram, it's represented by a dot, right? So let's go to the document. I'll resend it. Uh, I'm having a problem. I don't have. Wait, nah. Let me just do this. Uh, oh, flipping hell. Um, can I give it time? Um, okay, yeah, free body diagram. That document. The then wait, forward, forward. Physics grade 11. Okay, I just re-forwarded it. Nah. That document that I just sent to the group. Like, can we look at it, go through it, so that we know for a fact we once did free body diagrams. Okay, fine. As I was explaining, a free body diagram, it's a representation, right, of all the forces acting on what? On an object. And I need us to understand one thing. Let's say we have a table. This is a table, right? And it has an object over here. Before we even know about the forces applied and everything, we should know that there's weight acting on it. This weight, which is just Fg, the gravitational force that's pulling. Wait. There's a gravitational force that's pulling the object to what? To the center of the earth. And there's always a normal force acting on the object. This is Fn. These are the two forces that we know they're always on an object, provided that the object is sitting on a not on a table specifically, but if it's sitting on a surface. We have Fg, we have Fn. It's guaranteed. Do you guys understand that? So now I'm going to need us to look at uh the what do you call it? That document that I sent. Did you guys see it? The one that I just resent again. So that the people that just entered, they know what I'm talking about. So let's look at the first diagram. First diagram, I think this could be like a table or something. And we have an object over here. It's just lying here. I'm saying if an object is lying like this, it's not in motion, nothing is happening. We should know that if we draw a free body diagram, these are the forces to expect. We have Fg and we also have Fn. This is the normal force. This is the gravitational pulling it down. So if you draw the free body diagram of this over here, you're going to have a dot, right? representing the object, and you're going to have FG. You have to show the direction of the FG, because if you just say FG and it's like this, we don't know where the FG is acting, right? So this will be your FG and this will be your FN, right? So another way in which they can put it is that, so this was A, right? Now let's say this is B. Another way in which they can put it is, let's say you do again have a suffix like this, and you have your object all this way, but now this object, what's happening? You have force that's being applied. So you have FA going that way. Okay, remember, again, let's say it's maybe a string attached. Yeah, let's say it's a string attached to this block and you're pulling at this angle, right? Fine. When you draw your free body diagram, um, when you draw, listen and listen attentively. When you draw a free body diagram, you do not have to break down the force applied into its components. You are going to be incorrect. Your marks will be deducted. So when you draw a free body diagram, we know that this, okay, fine. This is how the correct way to do it. Ne? You're going to say your dot. We said if it's sitting on a surface, we have Fn going up, right? And then we have Fg going up, going down, sorry, right? Then we can see that this Fa, it's applied, why? It's not like straight, it's applied at an angle. So you could just do this, and this will be your F applied. What I was saying is that resist the edge to do this, because you're going to be incorrect. They don't like it. Like, let's say your Fn, right? And you'll have your Fg. And then you want to break this Fa into what? Into its you want to break down this Fa into its components, whereby you say, let me just do this. Like you say Fa cos of whatever angle. Let's say they give you that this is 20. You say Fa cos 20, and then you say this is Fa sine 20. When you draw a free body diagram, don't do this. Nah? Yeah, guys. Just put it like this. This Fa, put it like as one thing. Don't try and break it down into its components, right? So you see how your um, free body diagram would look if you had an applied force, right? Now let's try and do one. Let's say now you have a box that's floating in air, right? It's floating in air. So you have 3n, you have uh, 2n, you have 5n. So these are all the forces acting on the box, right? One it's going that way, then another one going that way, and then the other one going that way. This box, remember I said it's what? It's floating. It's just in air. It's not on a surface. So it does not have Fn, right? If it's not lying on the surface, if it's not lying on the surface or on the ground or whatever, it does not have Fn. So this is floating. So this is how your free body diagram would look. Let's look at this three, right? Let's take them one by one. This three, as much as it's coming from below, it's acting in the what? In the upward direction. So this three would be where? Here. So it would be 3n. Now let's look at this 2. It's pushing the box to the left. So it's acting in which direction? It's acting in this, the left direction. This is the 2n. Now let's look at the 5n. The 5n, it's acting towards the right. 5n. And remember, we said this box, it probably has like a mass of, like, I don't know, anything that has a mass on Earth. Anything and everything on Earth that has a mass, it's experiencing what? A gravitational pull. So we will have Fg acting in this direction. Do you guys get it? Okay. Then let's say we have an object on a rough surface. Once they start adding words like it's a rough surface, you need to know that that object is experiencing what? frictional force. So let's say they have, it's a thing, this is the rough surface, right? And then you have a box over here, and then you have your FA going that way. All right. Fine. Now you have to draw a free body diagram of all the forces acting on here. Remember, it's on a surface. So the free body is going to look like this. We're going to have Fn because it's lying on a surface. We will have our Fg. We will have our force applied. And remember, we said it's a rough surface. And the frictional force will always act in the opposite direction to the force applied. So if the force applied is going to the right, it means that the frictional force will go to the left. So this will just be your FK, right? So now let's look at okay, let's look at these when they're on an elevated surface. You have, oh, wait, I forgot to mention something. Ne? Remember, we said we have Fn. This Fn, it acts at a 90-degree angle to the surface. Hence, it's going upward and straight. It's at a 90-degree angle, this Fn. You'll never draw Fn, and if it's on like a surface that's like this, and it's going that way, and then you say this is Fn, you're going to be incorrect. Your Fn, it always has to be at a, sorry, just assume that this is 90. It has to be your normal force, it always has to be at a 90-degree angle to the surface, right? Note that. So we have another example over here. So they're telling us that mm, we have FA. Okay, fine. And they're telling us that we should draw all the forces acting on this object over here, right? Okay, fine. Free body diagram. Okay, what I normally tell people is that if you have an elevated, because you can see that this is acting at an angle, right? Let's say this is 30. If you have an elevated angle like this, like 30, take your pencil, lightly draw the slope, right? Like not the slope, the steep. Lightly draw the steep. Can you guys see what I'm doing? Let me see.
Yes, ma'am.
Okay, lightly draw this. Okay, lightly draw the steep, right? And then where your object is, because it's a free body diagram, you have to do what? You have to put a dot. Remember what we said about FG? FG, it's pulling the object to the center of the earth. So it's always acting what? Downward. So this FG, as much as this is over here, FG will go downward like this. Right. Now we have Fn. Our surface, unlike the previous time, our surface was straight and we just had this. And we said Fn is acting at 90 degrees to the surface. Now let's look at this surface. This surface, it's no longer straight, but it's here. So this Fn, see over here, the Fn was acting at a 90 degree. Even over here, the Fn has to act at the 90-degree angle to the 90-degree angle to the surface. And here's our surface over here. So which means, I mean, if you want to be accurate, you could just say it. So our Fn will go, this is Fn, right? And this will be your Fg. Now let's look at our Fa. Our Fa is just going in the upward direction. So our Fa will act that way. What I wanted us to notice and know is that even on an elevated slope, the Fn, it has to be at what? At the 90 degrees angle. Do you guys see that? Then this will just be our Fa. Do you guys see that? Then you can just afterwards erase this, because this was just to make you accurately draw what's happening here. But can you guys see what's happening? Like how you would draw the free body diagram of this over here. Can you guys see that? You guys understand this? Hi. Okay, Sheila. I think um Sheila, you raised up your hands. Do you have anything to say? You can say it in the chat, provided that you can't unmute yourself. Or was it a mistake? Okay, but do you guys understand like the free body diagram of this?
Ma'am, the FG there, it makes sense, but then the other two, I don't understand.
Okay. Okay. But wait. Um probably not. This one you understood it. No, not this one. This one you understood everything. Where is it? This one. Like why it's like this, because we have FN and FG.
Yes, ma'am.
Okay, remember, same thing here. This was our surface, right? This FN, it's acting toward at the 90-degree angle, right? This one, do you understand it? This is our surface again. The FN, it's acting at the 90-degree angle. Then the F applied, it's just at an angle. Because here, it's not put directly like downward. It's said to be acting at an angle. Hence, we put it down here. This, do you understand?
Yes, ma'am.
Okay, great. As long as you understand those two, means you're in the right path. Now, if we have, so they're telling us that, okay, remember I said Fn, which is your normal force, it always does what? It always acts at a 90-degree angle to where the object is. So if this is a slope, right? Remember 90-degree looks something like this, right? It looks like this. So if this is a slope and this is our object, and we're saying, okay, let's identify. Firstly, let's identify all the forces acting on an object. We have this FA. We have the normal force, which is supposed to act what? At the 90-degree angle. So if you have the time, you're going to take a protector, put it over here. Try and check where your 90 degrees would be. This is your 90 degrees. This is where your 90 degrees would be, right? Let me just remove this and just. So if you draw a force, it would be going that way. This, if you measure it, it's supposed to give you 90 degrees. It's your what? It's your Fn, because remember we said Fn acts at the 90 degrees to the surface. And over here, this is our surface, right?
Yes, ma'am.
Okay, so we've established that this is our surface because this is where the object lies. So Fn acts at the 90 degrees to the surface. So you have to put Fn where at the 90 degrees to the surface. But we also know that we have the weight, which is Fg, pulling the object how? Downward. You should never ever make the mistake of pulling of putting the weight like this. Okay, let me use a pencil so I can erase. Like this. Because this is not downward. This is just the opposite of Fn. Downward would have to be this way. So now, if you try and draw all the forces acting on here, this is what you would have. I'm saying, for accuracy's sake, just likely draw the elevated surface so that you don't make a mistake, right? This is the elevated surface. Then, remember, we're doing what? A free body diagram. And in order to have this object, we'd have to put what? The dot, right? Now, let's look at this. We said Fn acts what? At the 90-degree angle. So our Fn, it's most likely to look like this because this now forms a 90-degree angle with the surface. Remember, this is our surface, right? Now, look at where Fa, force applied, is going. Look at that force applied. It's going where? Up. It's pulling the object up. This is our up. This is where the object, the FA, it's acting, the direction in which it's acting upon, right? This is FA. This is FN. Now, remember we said FG pulls what? FG pulls FG pulls, what do you call it? It pulls the object towards the center of the earth. It pulls the object how? Downward. So this would now have FG as the downward force. This would be FG. This can erase this. Then afterwards, we just erase our surface because we drew our surface so we could draw our forces accurately. Do you guys get this? Now,
Yes, ma'am.
oh, okay. Does everybody get it though?
Yes, ma'am.
Oh,
Yes,
okay.
ma'am.
Thank you very much. Um, I think for interest's sake, let's do the last one. This will be the last one. Okay, yes. Yes, definitely this one. So we have now an elevated slope like this, and we have, remember, look at this FA. It was acting parallel to the surface, right? It was just straight. Now we have FA at an angle. Now, how would you represent this? Before we even try to represent this on as a free body, let's just identify all the forces acting here. We have Fn, which is going to be acting at the 90 degrees angle to the surface. We have let me just write it as Fn. We have Fg pulling it down. And we have FA acting at an angle, right? So remember I said when you draw a free body diagram, firstly try to make the elevated slope, but make it light so that at the end you may be able to what? To erase it, right? So if this is like this, uh, in order to represent this object over here, you're going to have a full stop like this, right? Now let's put all the forces that are acting on here. We have Fn, which will be acting at a 90-degree angle. Remember, right? This is our Fn. Then we'll have Fg, which is just pulling it downwards. Then this is Fg. Now let's look at this Fa. This Fa, it's acting at an angle. Remember this Fa, it was parallel to our surface. Hence, we just put it, because this was our surface, hence we just put it going there. But this one, it's acting at an angle, right? And if this is our surface, the imitation surface that we drew to remind ourselves, this is the imitation surface. If it's at an angle, it means our F applied will be somewhere here. This is our F applied. So you erase this part, you erase this part, you erase this part. Okay, sorry, this has to be like directly downward, guys. I get telling you why is it skew. This is just down like this. This is F, G. Okay. Can you guys see it now?
Yes, ma'am.
Okay, great. So this is how it would now look. Um, yeah. Um, let's do another one. Last one. After this, we're done. So let's say now there's two objects, right? We're working with two things. We have A, we have B over here, and it's going like this. Now, okay, fine. We have A. Let's look at A. A, it's lying on a surface. What does that mean? It has Fn. It it has Fg. Now let's look at this. This is tension because there's a tension in the string. Okay, this is the string and this is like a pulley. This is also a string, right? So here we have tension. So if we look at all the forces acting on A, it's normal force, gravitational force, and the tension, right? So if we have Okay, sorry. We're trying to do a free body diagram of all the forces acting on A, right? Um, we're going to have Fn. Remember, it has to act at what? A 90 degrees angle to the surface. And since well, our surface is just a flat surface, it means it will go upward. So this will be our Fn. And going down like this, we will have Fg. And to this direction, we will have our tension. So this is the free body diagram of what? Of A. Now let's look at what B. B, it's just suspended in A and it's being pulled up by this rope over here, right? We have a rope. And this rope, it's exerting what? It's exerting tension on it, right? So for B, if you draw the free body diagram, it will just have FG and what? And tension. Because every object that has mass has FG. And the tension comes from the rope. Do you guys understand and believe that? Did somebody write a message? Oh, it was Sheila Kikana. Yeah, but do you guys get this?
Yes, ma'am.
Okay, great. We have come to the end of our lesson. So, and the next one when we meet, we'll be doing Newton's laws. Yes, then we'll move on to chemistry. So, thank you guys very much for joining today's class. Nah, see you when I see you. Bye. Clap, clap.